today we are going to do a system design. That is to design a parking lot. So as a system design, usually when we design a software system, we want to consider a few basic elements. First thing, we want to understand the requirement, usually like the functional requirement, what the system will do and can do. Another part is like a non-functional. It's like reliability, consistency, etc. And usually when after we clarify the requirement, we can think about like how big the data size is, what's the system load, expected load, and then we start to design some component, basic component. Depending on preference, you can the system design first, or we can start from data, or if you like the object-oriented design, you can also start from the OOD first. So here for the parking lot, as we all can see, the parking lot itself, what's the requirement for the parking lot. So the basic thing is for the parking lot, think a parking lot as a parking building, a parking tower. It probably have 50 floor. You can do the parking, and each of the floor they may have like 20 cars that can park, 20 spots. For this requirement, we need to think about, okay, for this parking building, we need to do the show the available parking spots in the building. Usually you can see a bulletin board say we have 20 available spots you can park your car, so you make sure it's at green. Else, if the parking lot is full, it's sorry, we do not have any space. So if a car is trying to park into the garage, it says we need at least to park a car and into a parking spot. And afterward, the user may pay the parking fee, and then drive out. That parking space will become available again. So the requirement is quite straightforward. I mean, that's for the basic requirement. There are some additional requirement for the system. It's like user may need to log into a system. May probably have a mobile phone application, so the user can actually manage their own parking, or the user can log into the system and the parking lot and the application. They both can do some authentication, so that after authentication, the user can, for example, from the phone or either from the gate, the parking lot gate, they can authenticate with the parking card. I probably be a member of the parking lot. So in that case, we may want to have more management system, and of course there would be at least an account management system. The account means the user account, and also there will be connected to a accounting system, which is depending on how you make your payment, and you charge your money, and maybe keep your credit card information, etc. There's some additional requirements. But for the basic requirements, think about the parking system. We need a few things. So first thing is a non-functional requirement. Think about the parking system. We want it to be very, very reliable. Data is very consistent. We do not want to show the wrong number on the bulletin board we do not let the driver spend 20 minutes drive into the parking lot and say, oh, sorry, we do not have any available space. That would be very annoying. And whenever a user make a payment, I want to make sure we charge the right number, else we get a lot of phone calls. I want to make sure the data is very consistent, and also we want it to be high responsive. And high responsive means like if the user swipe their card, or even the user, for example, the user want to get into the garage or want to get out of the garage. We do not want the user get blocked anywhere. At least get some response in a second, or at most like 2 or 3 seconds. Else user may be annoyed. And for the scalability, that can be an issue, but usually not for this case, because as we talk about the data size, like you have a 50-floor parking lot that probably can be 100 spots, 1,000 spots. I mean, and for each spot, it may have few swipes per day, but I don't think it can be more than 10 swipes. So for a tall building or parking lot, we may probably have only 10,000 transactions per day for whole building. That is not too much load for a modern system. We can easily just put it in a SQL server and the web app, a microservice. You can have some kind of scalability. It should be work yearly. But we want to make sure the system to be more reliable. That like if one system is down for whatever reason, like a data center powered off, or the AWS or Google Cloud service gets down, we want to make sure the system still can be accessible. Especially at midnight, when they make sure it work like 24/7. Always working. That's very important. Because even if the system goes down at midnight, it will be generally more cost for the human hotline support. We rather make the system stable inside. So for the system design, I'll go to another use Google Drawing. From here, I have a drawing here, for the parking. There may be multiple different clients. You probably have a phone client. The user use a phone to manage their parking, and also there probably a bulletin board, like a dashboard or whatever, to show how many valuable spots inside this parking lot. And for the we already have a gate. The gate is in front of the parking lot. There's a gate to authenticate the user and get a payment. And then after you take a parking ticket and you go to the garage, let's say the gate. So the gate check the real traffic. So most of the design here, we are mostly talking about think about as the gate is checking all the traffic in and out to the garage. Suppose there is a car driving into the garage, so it goes through the gate. Then it goes through. It always goes through the gateway. This gateway is the system gateway, not the physical one. And for this gateway, they'll do some. If they need authentication, they'll do the authentication, and then it'll go to the microservice. The microservice will, for example, when they park the car, and parking service to call the service park the car and then let's say update data into a database. Then the database will update the record, and as I said, we want to make the data to be the database to be more reliable, and it's especially we do not want to have one database go down and the system crash. So at least they have you have a primary database, another secondary database. They can be all write database. I mean, they serve as the secondary database serve as backup. I mean, this is not a write database. This is a write database, and this is not a read-only database. I mean, here we can have different design. For example, we can use a primary two write database. They sync the data each other, and then we have a read-only database for each of the write database. But we can also think, okay, now we have only two databases, primary and backup. For the whenever the primary get down, the backup will turn to the primary and serve as a write database. And by default, it can be a read-only database. So we can have different design for this purpose, but the key point here is we want to make sure the system, whenever a database get down, it can be the whole system can still work. For the that's the key thing. It's not about load; it's about availability. For the parking service, whenever they are parking, whenever we park the car, they will go to the. Also, you already check the accounting service, like when you check out, we'll check out how much money I should charge you. For that one, it can be at least for some basic feature, like when we check out really mixed payments, I'll check how many balance you have in your account. Probably have some credit. That would be we can say that's maybe an accounting service somewhere. But we can manage the pricing strategy inside the parking service or inside the accounting service. So you can think about different strategy, but here there are some another logic here. And so similarly, the load to the accounting service is not high neither. But the accounting services have shared a similar strategy to be most available. We don't know any data to be wrong. So that is about the system design from a system component. I did not realize here we need too much like caching or whatever because we mostly want to have the system to be saved database in real time and the data be queried from a single source, so that we can spend less effort to manage consistency. So the consistency is one of the most important features we want to have in the system. Now go back to the detailed design, like we design class. So first we need to design a class called parking lot. The parking lot, I mean, like the parking building, the parking tower, they have 50 floors, for example. In the parking lots, inside for example this building, there will be a list of parking spots, and for the method, we may have a general method called available spots. Like that means how many spots we have, available spots we have. Another method is like a park a car, remove a car. When we park the car, we actually, what it means is find available parking spots in the parking lot, and then say park, and then we call the method for that given parking spot, say, okay, you park a car over there, and remove a car to do the same thing, find the parking spot and then remove the car from there. So that would be if we add some more detail. Park a car is I would say license plate that will be given a car. I mean, they should use to identify the car. Park a car, license plate, and the car type. And the car type can be like a compact car, regular car, or truck. I mean, oversized car or probably electric car. Then it will go find a parking lot, and then they also do the detail logic inside it. When I do a removal car, the removal car I need also need a given license plate. Say, okay, I need find where your car is, because I mean that depends, because if I mean think about the if there's autonomous parking lot, so when the user try to say I want to get my car, and it can, because for example the client or the system may know both data, including the license plate and also the parking lot, the parking spot location. So, but basically here I would say assume we use the license plate and to find the car and the parking lot, the parking spots, and then remove the car from that. So then down to the details, we have the parking spot here. The parking spot means, okay, the parking spot is one parking space. So we would know there are a few things. One is where the parking spot is, like the floor, or probably a label. Depends. We may say the floor is like first floor, second floor. This would be an int. For the label, for example, what I mean the label is like 3 floor, D area, number 20. This is they probably have some other different label, but what I mean is the label is a string. The space size, I would say space size, that is what I mean is like square feet. That's a float. That's a float number. And then I may want to have another. I mean, to keep consistency with the idea, I would say parking spot ID, and that will be an int. So that may be easier for me to identify that. And for the space, yes, I need to have know how big the area is for these parking spots. That's a little bit redundant, but because I have the type, the type is a enum. They may tell this is a motor circle space, or compact car, or even truck, or probably electrical. I mean, it's available. That is another. It is another key. Member, which it means if this parking spot occupied or not. Yeah, this is one of the key things we want to manipulate. So default, we can say it's true. For each of the parking lot, it will be two different methods. So first thing is I would try to add another three, like license parked car. So as this actually say license plate number. Yeah. I mean for this, this is optional. This is optional. We can put it in this class, or we can create a separate management class. But I can put it here right now. For the method, I can have like this would be actually called by the parking lot class, or we can call it as a parking lot manager. So the parking lot manager actually doing the front end work to like, okay, I will go, you need to park your car. I will go find the parking spots, and then the parking spot will do the real work like license plates, park the car. You pass the I will pass the license plate and park a car here. So the parking car, we do not need a car type because itself has only one type. So now those are the basic characters, the method and the members properties for this class design. Now we want to try to map the class to a database. And yeah, that's how we store the data. So the database design, I assume like for example is MySQL, any SQL database. For the given parking lot, parking lot I want to keep actually a slightly different structure because we here in the database actually we only keep the basic information like parking lot ID, for example address, total capacity, and this is a little bit redundant. We already do not use this field because we want to show the real-time capacity mostly from the parking spots table. But here we may keep the this like a meta info. They probably have other meta info. Okay, we do not keep a list of parking spot inside the table because that would be in the parking spot table. For each parking spot, of course it will connect to a parking lot ID. This is how we correlate those two tables. And for each of the parking lot, we know like whether location, which floor, we probably have a label, similar as how described in the class, like 3 floor, D area, number 20. The space like a square foot type is available or not. Or the parked car, license plates. Yeah, this is most of the feature we have. And in the parking, we want to keep another. This can be a table, or this can be another like a NoSQL DB. But in terms of size, the data size, most likely we can keep track of the history inside of the SQL table. So what I would do is like keep the license plate and check out. I mean, this car actually parked into the parking lot and the parking spot. Okay, this car parked in this parking spot from time in to time out, and how much they actually paid. So we may keep some basic information so that in case the user may call the service hotline and say, why did you charge me the wrong number or not money? So we need to keep track of the history, and also we need to keep the information to track, do the analysis. And we need some index, including index on the time, index on the plate, and for the parking spot, the index may be also quite simple. We want to have the parking spots and parking lot ID. That's something we may want to locate it. But there's another maybe most important query: the parking lot ID for this given parking lot. How many? So it's basically say available. How many parking lot available? I mean, those are based on the frequency of the query. Like parking lot ID, they always have that by the type and available. So the use case like, do we have a parking lot for a truck? Something like that. So we need a type as well. So I mean, we may have more information for that. We may add more index if we need more different queries. And but for this one, parking lots, we may most like unique auto increase. I mean, unique index. I mean, that's maybe all we want. So now we finish the database design as well. We work through the logic. When we have the basic system working. So I may probably want to have some auxiliary system component for the system. For example, we have the parking history. For example, we have the parking history. Let me maybe create another database. That's optional. You can have a database, or probably just one table over there. What I mean here is for each of the parking event, I'll keep the history. And when you get the history, we want to do some analysis. Sorry, let me give you a different name. Analytics. And plus the dashboard. There is another. Okay, I do not want to go too much detail, but I mean, we need a lot of analytic work. We'll probably show a few different reports. For example, we plot the parking history for each of the parking lot. Say how many cars park in this parking lot every day, and we want to know our revenue every day. That would be mostly from the parking history. That is, we can have different strategy for that. But internally, that is not a real-time thing. As long as we have the report in time, that will be good enough. Yeah, I think that's most of the component for the parking system design. So I would say, if we want to make a system more clear, we will say this is autonomous parking lot. So it's like everything happens when we try to park the car, and you just put your car around the gate or parking lot, and the parking lot itself autonomously parking a car somewhere. So that may make the function more clear. So the system itself would manage everything. So that's how basically this system is working. If we need to track more information, like the user may park their car by themselves, and that be a little bit more complex and a little bit more uncertainty, because it's a little bit hard to track where the user actually parked the car. For example, the user may drive a compact car, but he probably just park the car at a space where it's supposed to park a truck, so you cannot monitor all the setters. And the user may move their while they're parking the car inside the garage, he may move their car from one parking spot to another one, but he did not drive out, so the system do not know that. So that can change. So in this situation, we may want to try to reserve the a lot of parking spots to make sure when the system will not give some misleading information for the user, and for the user, the system think the other truck's parking spot over there, but they actually occupied by a compact car. That is, when the user actually drive a truck inside, he cannot find a empty truck parking spot. That is annoying. So in that case, we may need some kind of human interaction, or we may need some extra monitoring system. But that's something just a further discussion. So for this use case, we mostly assume that is autonomous driving, autonomous parking lot. So to make the system simple, yeah, that is about the autonomous parking lot system design. Thank you for watching.